Proving trigonometric identities and rearranging trig expressions can be one of the most frustrating and yet also one of the most satisfying and rewarding aspects of A-level maths for a lot of people. All of the creativity that's required within that topic is also required in integration, where a lot of the time you'll be looking at an integral which you cannot evaluate and trying to find an appropriate method that will allow you to convert it into a different looking integral, which is something you can evaluate. Often the two things combine into one and the same. You're dealing with a tricky integral which perhaps can be more easily evaluated if you can find some way to rewrite the trigonometric expression inside. In order to be able to get to that, we first need to know how to integrate each of the individual trig functions. Now, a couple of these ones you ought to be able to integrate directly, either because you remember them already or because you can work backwards from derivative results. The others you're going to need to look up in the formula book. So when you've written down a result for each of these, then we'll go through them one by one. So sine integrates to negative cos x plus a constant because minus cos x differentiates to sine x. Another way of saying that will be cos x differentiates to minus sine x. So that's the derivative result that we're working from. Similarly, cos integrates to sine. For the next ones, you're going to need to look in your formula book. So have a look at page 7 and you'll find a table of integration results, most of which are going to be trigonometric. So we can see these first 5 in the list are all trig functions of one sort or another. Sine and cos don't appear in that list, but tan does. So we can make use of that fact. We've got tan integrating to ln of sec x plus a constant. Sec is there as well down at the bottom, so we can generate that result. And cosec, that one's there too, minus ln cosec plus cot, and finally cot x, which integrates to ln of sine x. Now, you might be wondering why those four give such strange integrals, and in particular why they involve logs. You could prove them directly by differentiating the right hand side, and that would show you that they are true, but it wouldn't necessarily show you how you would integrate. When we get to the integration by inspection section, we will look in more detail at how we can derive a couple of these. Some of them take a bit more work and a bit more trickery than you're likely to easily come up with on your own, but they're worth looking into. In general, if you need to use them, you are perfectly at liberty to quote them directly from the formula book. So anytime you can turn an integral into something that just involves single trig functions, you're home dry. Next, let's look at the squares of all of the trig functions. As you'll see, a lot of these also in some form or another appear in the formula book. You need to look at both page 6 and 7 in the formula book because there are some results that appear on the integration table, but others that don't appear in the integration table and yet do appear on the right hand side of the differentiation table. See how many of these functions you can integrate. Right, I'm going to dive in with sec squared. That's the first one I notice in the formula book that I have in my list that I need. So we can get the integral of sec squared, and in fact it also appears in the differentiation table. So just in case you're looking at one and then the other, this one's going to appear in both, so you're definitely going to spot it. Cosec squared, however, does not appear in the integration table. Fortunately, it does appear in the differentiation table. If you differentiate cot x, you get minus cosec squared x, which means if you integrate minus cosec squared x, you get cot x. And if you integrate positive cosec squared x, you just get the negative of cot x. For cot squared x, that one doesn't seem to appear in either of the two tables. And tan squared is the same. We've got a bit of a problem with those two. But it's only a little bit of a problem, because if you recall, there is a direct connection between the squares of every trig function and another one. So sine squared and cos squared go together. You can add sine squared and cos squared, you'll always get 1. So you can convert sine squared to 1 minus cos squared. You can do a very similar thing with tan squared, converting it to sec squared x minus 1. And as soon as you do that, you can make use of the result below for sec squared x. Similar thing happens with cot. Cot squared x can be rewritten as cosec squared x minus 1, so we're taking advantage of that standard trig identity to rewrite it in terms of an integral that we can find somewhere in our formula book, somewhere in the standard results as they're called. The only two we're left with are the two that you might have imagined should be the easiest ones. How do we deal with sine squared x and cos squared x? They are not provided in the formula book, neither in the differentiation table nor in the integration table. So let's take a look at these two and see if we can find a way in. We're going to need to consider identities that will let us convert these integrals into something that can be integrated. What's the big problem? Why is sine squared causing us such a headache? Well, the main issue here is that we have a chain of functions, but the function on the inside is not just 3x plus 7 or ax plus b. It's not something linear. So we can't do the standard approach of just reversing. If we were dealing with sine of 7x minus 9, well, we just integrate it to get minus cos of 7x minus 9, and then we divide by 7. But we can't do that here because this is sine x being squared. The inner function is sine x. So it's not something we can just directly reverse. So the next question is, can we rewrite this integral in any other form? And the most sensible toolkit we have at our disposal here is trigonometric identities. For tan squared and cot squared, if you remember on the last slide, we were able to convert tan squared into something involving sec squared, which appears in the tables, and cot squared was able to be converted into something involving cosec squared, which also appears in the tables. So perhaps there's an identity we can use to help us with sine squared and cos squared. Have a think, see if you can come up with anything, and when you've given it a go, whether you've managed to succeed or you've hit a dead end, once you've had a bit of a work at it, come back to the video, let's see where we go. I'm guessing most people started by writing down sine squared and cos squared is identical to 1, which is perfectly valid and true, but it doesn't help us. It does give a link between the two integrals, because if you knew how to integrate sine squared x, then you could integrate cos squared x because it'll just be the same as sine squared, just with a 1 minus sine squared x. So you could make use of one of them to work out the other one. But even though it gives a connection between the two, it doesn't give any direct way in. It doesn't let you find either of the two integrals. So are there any other trig identities? We're going to have to cast our net a bit further afield. We've looked at the sine squared and cos squared. The other derivations of that involve tan squared, sec squared, cosec squared, cot squared. What else do we have that might involve a sine squared or a cos squared? Well, this is where double angle identities appear. These are really, really helpful for this type of question. Sine 2x doesn't help directly in this case, but if you ever come across a sine x multiplied by a cos x, this is a really quick, efficient way of converting that, the product of two functions, each of which on their own will be fine, but as a product is a little bit of a tedious process to follow, even when you learn integration by parts, which allows you to deal with products in certain situations. This particular product you could do with integration by parts, but it's going to be tedious and long-winded. It's much quicker if you recognize that sine x cos x can be replaced with a half of sine 2x, and sine 2x will integrate like a dream. In this case, though, we might find it more useful to have the cos 2x formula. This one involves the square of cos and the square of sine. In fact, we can rewrite it a little bit so that it involves only the square of cos or the square of sine, whichever one we need for our particular situation. There's a bit of rearranging needed. We want sine squared x, for instance, and we've got an identity that has cos 2x as the subject. But if you give it a rearrangement, you should be able to rewrite the two integrals and then integrate them. So try that, see how you get on. Hopefully, you've managed successfully. Sine squared can be rewritten as 1 minus cos 2x all over 2. And the 1 over 2 integrates to x over 2. And the minus cos 2x over 2, we still have the minus and the half, but then cos 2x will integrate to positive sine 2x, divided by 2, the derivative of the 2x. So we have to take that into account when we integrate something which is a function of something linear. It is pretty easy to deal with cos 2x. We just have to make sure we turn it into sine 2x and then divide by the derivative of 2x. No surprises that the cos squared x integral should come out looking pretty similar. In fact, because we've used cos 2x for both sine squared and cos squared, we end up with a very similar looking integral, and it comes out with the only difference being the sign in the middle, 1 plus cos 2x or 1 minus cos 2x all over 2, which means it's either x over 2 minus a quarter of sine 2x or x over 2 plus a quarter of sine 2x. You might notice that if you add these two integrals together, the minus a quarter sine 2x and the plus a quarter sine 2x cancel each other out, and we're left with x over 2 plus x over 2, which is just x, plus a constant, potentially, which will be the sum of the two constants from the two separate integrals. And it makes sense that we should get a total of x, because if you add the two integrals right at the beginning, you're integrating sine squared x plus cos squared x, which is the same as integrating the number 1, and that should give you x, or x plus c. The next thing I'd like you to have a look at is the trigonometric integration bingo. This is the worksheet that I've prepared. The idea is you're practicing how you integrate the product of two trig functions, because it's not just sine times sine and cos times cos or sec times sec that you can integrate, but actually if you have sine times cos, we've already seen that you might be able to use a double angle formula for that. The others require different techniques. You might find these identities useful. There's nothing else you would need apart from creativity, these trig identities, and of course being aware of which results are provided in the formula book. There's a couple we've not explicitly used yet. Sec tan integrates to sec, for instance. Cosec cot integrates to minus cosec. Those results are not provided in the integration section, but if you look carefully, you'll find them in the differentiation table. So have a go at this sheet and see how you get on. If need be, you can look at the hints that occur on the following page, and then when you're ready and you think you've got answers, you can either check them with Wolfram Alpha, or you can look on the final page which has full solutions squeezed into the boxes for you. We're going to finish off with an example. This was a question that I picked out from fairly early on in the exercise that you're going to be working on, question 2i. So thrown in there amongst a bunch of other similar-ish looking questions, it should be the kind of thing that can be readily dealt with using the trig identities that we've got. The reason I included it is because when I looked at it initially, I couldn't immediately see what to do. In fact, a bunch of different unhelpful things ran through my mind before eventually I got to the point where I could see what was happening. Perhaps you've looked at it and you've immediately noticed something that's going to make it simpler, in which case you can feel smug because you spotted it before I did. But I was looking at the cos 2x on the top and thinking about changing that. I was looking at the cos squared 2x on the bottom and thinking about how I could rewrite that as something involving cos 4x. There are lots of options here, but none of the options that I initially thought of would have helped to turn this integral into something nicer. Let's start by asking ourselves the question, why is it difficult? If we're finding it difficult, what is it about the way it's written that makes it difficult to integrate? Well, for a start, although cos 2x on its own would not be a problem for us, cos squared 2x is tricky because of the squaring. So it's not just a function of something linear, it's a function of cos 2x. It's a cos 2x that's been squared. So it's not something you could directly integrate, even if it was just sitting on its own. You'd have to do something sophisticated with it. The fraction is the thing that really puts a spanner in the works. Anytime you're trying to integrate a fraction, you're going to have some issues. There are all sorts of different approaches you can use, and one of the later videos I'll show you will look at a few different fractions that look very similar but might have quite different approaches, and we'll think about the kind of things you might look for. In this case, for instance, you might even notice you can factorize the denominator of this fraction, but even that doesn't help you much, because even if you can split the fraction apart, you'd be left with two awkward fractions, both of which are difficult to deal with. Can we find any way to simplify this fraction? Clearly, factorizing the bottom is not going to help us much because there'll be nothing that cancels with the top. But are there any identities that we might find useful? Well, here's a few of the obvious ones that we should write down. Anytime we're dealing with double angle formulae, it's a good idea to write down the double angle formulae so that we can see what we're working with. And of course, we have sine squared x and cos squared x equals 1. So obvious that you might not even write it down. I didn't. And that's why it took me so long to notice what was going on. So the first thought I had was, can we change the cos 2x on the top to something different? But if we change it, all we're going to be doing is making it harder to work with. We could turn it into cos squared minus sine squared, or 2 cos squared minus 1, or 1 minus 2 sine squared, but none of those are going to make life easier for us because you're just introducing a squaring that you didn't previously have, and you're losing the cos 2x, which on its own is not such a problem. What about cos squared 2x? This is one that often throws people. If you have cos squared 2x just on its own, you can integrate that quite happily using exactly the same trick we used for cos squared x. If you think about it, once you know how to integrate cos squared x, cos squared of 2x is just a chain rule situation with something linear inside. So you would integrate it the same way you integrate cos squared x, and you just divide by 2 at the end. Alternatively, you can get your double angle formula and then replace x with 2x, which means replacing 2x with 4x wherever that appears. You could turn cos squared 2x into cos 4x plus 1 all over 2. But that still wouldn't solve the fraction problem. If we tried replacing cos squared 2x with something else, we might get rid of the squaring, but we're going to be left with something that still has separate terms along with a cos 4x sitting around the bottom of the fraction. So the final option, the one that you may well have spotted right at the very beginning, we can replace 1 minus cos squared 2x with sine squared 2x. And as soon as we do that, we get a more sensible looking integral. Now the denominator is a single term, we have a decent chance of writing it in a simpler way. Now, anytime you see cos and sine squared involved, whether or not they're multiplied together or one of them is divided by the other one, or if it's cos squared with a sine, these generally combine nicely if you write the entire thing without any fractions. What I mean by that is take advantage of the reciprocal trig functions. If you have 1 over sine squared, I remember fairly recently being stumped by 1 over sine squared, trying to integrate 1 over sine squared x, and it took me quite a long time before I thought, actually 1 over sine squared x is just cosec squared x, and that one's in the formula book. So see if you can rewrite these involving sec, cosec, cot, things like that. There's a few different options you might go through, but when you find an approach that lets you write it out without any fractions, you might discover that what you've written appears in the formula book. Have a quick look there and see if you can guess which of the alternatives this is going to turn into. It might help if you just take some of the results from the formula book and rewrite them exclusively in terms of sine and cos. So then you've got something you might recognize more easily when you spot it in the wild. But in this case, we can break our fraction apart into 2 separate fractions multiplied, 1 over sine 2x and cos 2x over sine 2x. 1 over sine 2x is cosec 2x, and cos 2x over sine 2x is cot 2x. So we're dealing with a cosec cot, which does appear right at the bottom of that list in the differentiation formula sheet. Cosec cot integrates to cosec with a minus sign, because minus cosec cot integrates to cosec without a minus sign. So we need to make sure we include the negative. And the other thing we have to remember is to divide by the derivative of 2x. The only thing that makes this a little different to what's in the formula book is the negative sign. The k is actually provided for us in the formula book. So if you know that cosec 2x differentiates to minus 2 cosec 2x cot 2x, then we can divide both of those sides by 2, and we get a half cosec 2x differentiates to minus cosec 2x cot 2x. And therefore, put the minus in, and we've got exactly what we're looking at here. Now, you should be able to try the rest of 11c. Don't feel too bad if, like me, you come across an integral that should be straightforward once you know what you're doing, but maybe you don't spot it straight away. That's what integration is going to be like. And the more you learn, the trickier in some ways it will be, because there'll be so many more different things you might be expected to do. For now, you know for sure that anything you see in exercise 11C, you should be able to deal with by manipulating trig identities to turn it into a format that you either know how to integrate or you can find in the table. So that will help you a little bit, but you're still bound to come across examples that just completely throw you, or you just can't quite see a way in. So I'd encourage you to work through the way I did with this one. Try writing down suitable identities that you think might come in useful, and sort of hypothetically work through in each of the different ways. Even if you don't write it down, ask yourself, what would happen if I replace this with this equivalent thing? And then see if the result is potentially something that you can find in the formula sheet, or you can manipulate further to get something simpler. Enjoy.